Hi everyone. In section 1.5, we're going to discuss piecewise defined functions, or just piecewise functions, which are really useful in calculus. You often see these in the first chapter of a calculus book on issues of limits and continuity. A piecewise function is basically a function that has different rules for different subdomains, different x values. What's an early example of a piecewise defined function that we've seen before? I'll give you a hint. F of x equals x if x is non-negative, and it's the opposite of x if x is negative. What function did that? It was the absolute value function. So let f of x be the absolute value of x. What was the piecewise definition for the function? It was this. Like I said, the absolute value of x is x if x is non-negative. That is, if x is on this subdomain, bracket 0, comma, infinity, parenthesis. This is technically the subdomain. It's a subset of the real number line. Now, informally, I might refer to this as a subdomain because that directly leads to that. But technically, this is a subdomain. It's a set of x values, real values. So the absolute value of x, if x is in this set, that is, if x is non-negative in value, but the absolute value of x is the opposite of x if x is negative in value, if x is in this subdomain. Again, I might just refer to this statement. And bear in mind, I could have had a bracket here because the absolute value of 0 is 0 in either case. So for example, how do we evaluate f of 3, or the absolute value of 3? Well, because 3 is a non-negative number, to calculate this, we would use the top rule, because x is non-negative. If x equals 3, x is non-negative, we apply the top rule. The absolute value of x is x. As far as x equals 3 is concerned, we totally ignore this bottom rule down here in the case where x equals 3. The absolute value of 3 is just 3, because the absolute value of x is just x in this case. Likewise, let's evaluate f of negative 3. I'll do this in blue. What's f of negative 3, or the absolute value of negative 3? Well, in that case, negative 3 is a negative number, which means that we apply the bottom rule. We apply the rule f of x, or the absolute value of x, is the opposite of x, because x is negative in value. We're in this subdomain. Negative 3 is a negative number. We're in this subdomain here. So we apply the rule f of x, or the absolute value of x, is the opposite of x. We don't care about this rule. We don't care about it whatsoever if x is negative 3. Well, the absolute value of negative 3 is going to be the opposite of negative 3. And the opposite of negative 3 is positive 3. So the absolute value of negative 3 is positive 3, according to the bottom rule. The top rule is irrelevant as far as negative 3 is concerned. So basically, the value for x, the value of the input or argument, that tells you which rule to apply, and you apply the rule in order to evaluate the function at that value of x. Incidentally, the domain is the union of the given subdomains. The union of these, though, is just R, the set of all real numbers. Okay. But if you have a number for which you don't have a rule, then that number is not in the domain of the overall function. Here, we do have a rule for every real value of x. But if you have a value of x for which there's no rule, it's out of the domain. Well, how do you graph this thing? Well, you want to graph y equals x if x is non-negative. So we get this ray over here, starting at the origin, going through quadrant 1. But if x is negative, we want y equals the opposite of x. We want to graph y equals the opposite of x. And that goes through quadrant 2. So we get the v-graph. But it's a V-graph that corresponds to two different rules for two different subdomains. We had a rule for this subdomain, and we had a rule for this subdomain. By the way, in calculus, you're going to say that the function is continuous at 0, because if you trace the graph of the function with a pencil in the vicinity of this point at x equals 0, you don't have to lift your pencil. That's an informal way of looking at continuity. You'll make it more formal in your calculus class. One reason why piecewise functions are interesting is that they're often discontinuous. They often lose continuity, especially when they switch rules. You often lose continuity when you switch rules. Then something like this might be happening. And that's when things get really interesting. That's why your first chapter in a calculus book will often focus on piecewise functions, because you might get jumps like this where you have discontinuity. Next up, how do you evaluate piecewise functions more generally?